is tertiary carbocation is more stable than secondary carbocation, and secondary carbocation more stable than primary carbocation. As a result, the reaction that goes through a more stable intermediate would result to a major product, and the reaction would be faster. So when you want to study a reaction based on the kinetic or how fast the reaction will take place, you need to know the mechanism for reaction. So in this chapter, when we are talking about the substitution and the elimination type reactions, we want to study how fast the reaction is going to be. Depends on the nature of the substrate. The reactions are specific to alkyl halides. So when we're talking about alkyl halides, means that there's a halogen element from group 7A attached to a carbon that could be from the alkyl group or aryl group or vinyl group. So we have the halides. And compared to alkane, these compounds, they are a lot more reactive. And the reason for reactivity of alkyl halide is the polarity of the carbon and halide bond. Because halogen is highly electronegative, it's going to pull electrons. And when it pulls electron, so you do have a polarized bond. Carbon that carries the halide is going to be positively charged. When carbon is positively charged, it's known as like a nucleus. So what you find in the nucleus of an atom is protons and neutrons, right? So in the nucleus of the atom, you find the protons, which you have positive charge, and neutron have zero charge. So nucleus of the atom is known based on its positive charge. And then electrons are orbiting around the nucleus with different energy level. So when we have a positive center, that kind of represents a carbon with a positive charge. It kind of represents a nucleus. And if we have a nucleophile or nucleophile, it means something that likes electron. I'm sorry, something that like nucleus, nucleophile, something that likes nucleus. So if it likes nucleus, and what we have in the nucleus is a positive charge, so nucleophile likes positive charge. For some species to act like a nucleophile, it must be either negatively charged. Let's say you have iodide, has negative charge. So it can be classified as a nucleophile, is looking for a positive center. Hydroxide ion is a nucleophile. So we know that alkoxide is a nucleophile with a negative charge. So anything that has a negative charge, it can be classified as a nucleophile. You could have also compounds that they are neutral, like water, H2O. But because water has pair of unshared electron or two pairs of unshared electron on oxygen, because of the pair of unshared electron, it can share those pair of electrons with a positive center. So it's classified as a nucleophile as well. So if I label water as A and hydroxide B, which one is a better nucleophile, like a strong nucleophile, or A or B?
A.
B.
Okay, so
A.
okay, let me just explain one more time, because it's very important for you to kind of feel the definition or know the difference between a nucleus or definition for nucleophile. When we say nucleophile, it's something that is looking for positive center, right? If it's looking for positive center or a nucleus, then it must have either negative charge or it must have pair of unshared electron. We can classify nucleophiles as a strong nucleophile or weak nucleophile. I do have few examples here. So I just labeled water as A and hydroxide as a B. And the question is, which one is a stronger nucleophile? That means which one has greater desire to attack a center with the positive charge. So if you bring in, you had the choice of bringing hydroxide and water to attack the carbon with the positive charge, which of these would attack faster or more forceful or has higher tendency to attack the carbon with the positive charge? So if you are looking for a stronger nucleophile, which one is going to be stronger nucleophile? One more time, is it going to be A or B?
B.
B. B would be stronger nucleophile because has already a negative charge and doesn't like to stay with that negative charge, because when it has negative charge, that means oxygen has 3 pairs of unshared electron, right? In water, oxygen has 2 pairs of unshared electron. So if it's looking for a nucleus or a center with a positive charge and already has a negative charge, it would be a stronger nucleophile.
So the first thing you want to look for is the negative charge, and the second thing is the lone pairs.
Both. Let me give this example. Maybe I clarify what I mean actually by this. So alcohol has pair of unshared electron on the oxygen. We can classify this as a nucleophile. And alkoxide ion, that is alcohol after losing hydrogen. So if you remove hydrogen from alcohol, you would change that to alkoxide. This is alkoxide with oxygen carries the negative charge. This is also classified as a nucleophile. So if I label this A and alkoxide as B, both of them are nucleophile. One is a stronger nucleophile, the other one is weaker nucleophile, and nucleophile is attacking a carbon with the positive charge. Okay, so let's say this is attached to, let's say, CO, double bond, and is negative, and this is positive. So if you have a nucleophile, is looking for nucleus. What is nucleus? Is center with a positive charge. So this is the nucleus. Nucleophile attacks the nucleus or positive charge. Which one of these two, A or B, is going to be a stronger nucleophile? Which one is a better nucleophile?
B.
B? Okay, perfect. So did you see the difference and the definition for the nucleophile? Nucleophile is looking for a nucleus. So it's willing to share pair of electron with the nucleus with something that has positive charge or partially positive charge. And the more negative charge or higher electron density on the nucleus is going to make that on the nucleophile, if you have the negative charge, is going to make that a stronger nucleophile. So we have the nucleophile, and the nucleus is just the center of the atom, or representing center of the atom, which carries positive charge. So
So can every polar molecule be a nucleophile?
Then every polar molecule could be a nucleophile. Yes, if it has pair of unshared electron, yes, it can be a nucleophile. Yes, from one side of the molecule that carries a negative charge, it can be nucleophile, yes.
Yeah, okay. Gotcha.
So when we say substitution or nucleophilic substitution reactions, that means that you have to have a nucleophile coming in and forming bond with the like an alkyl halide and substituting this like a group in the molecule. So we need to know definition, what is the nucleophile, and then why nucleophile attacks alkyl halide? Because when you have alkyl halide, the halide pulls electron from the carbon that is attached to, and that carbon is going to be positively charged. So if you bring a nucleophile is not going to attack propane because there is no positive charge or positive center in this molecule. So if you add a nucleophile to this, there would be no reaction with alkane. But if you have nucleophile plus alkyl halide, there would be a reaction because in alkyl halide, you have that positive center. A carbon that carries a halide is positively charged because it's losing electron to the halide.
So basically, you just need a halogen there.
Yes.
Okay.
It's not just halogen, but this chapter concentrates on halogen. Any electron withdrawing group. The other example that I used before, it was like a CO double bond. When oxygen is pulling electron from carbon, oxygen would be negatively charged and carbon is going to be positively charged. So if you bring a nucleophile, it can also attack carbonyl group because carbonyl group also has the same characteristic, a carbon with a positive charge. Very good. So
Professor, what is it pulling from the carbon again?
why is polar?
What's it pulling from the carbon to make it positive?
Okay, highly electronegative element is going to pull electrons from the carbon.
Oh, the chlorine.
So, yes, chlorine is pulling electron or bromine is pulling electron. And as it's pulling electron, the carbon that carries the halide is going to gain positive charge. So we do have a partially negative, partially positive charge in the area that you have halide attached.
Got it.
So if there's a whole bunch of CH3, there'll be no reaction because
There
there's
would be
nothing
no
to pull from each
reaction,
other.
no. If you
Okay.
have just alkane, there is no reaction because there is no positive center here. Like the only type of reaction that we saw in chapter 4 was the free radical chain reaction. You had to have like a free radical that is very reactive to come and react with alkane, but substitution reaction, like displacement reaction does not happen with alkane, but it does happen with alkyl halide because alkyl halides are more reactive than alkane. What makes the alkyl halides to be more reactive than alkane is the presence of electron withdrawing group of halide that pulls electron from the carbon and makes the carbon positively charged. So you do have a polar bond in the in halide and in alkyl halide, but you don't have that in alkane. For every family that we are going to study from now on, we want to know about their naming, physical property, a unique property of that family. Like for alkyl halide, the unique property is that polar bond of carbon attached to halide. So that makes it easy for this and makes the alkyl halide a lot more reactive compared to alkene, compared to even alkyne. But for like, especially for like substitution reaction, it makes it a lot more reactive. So there is a polar bond in alkyl halide. We want to know about naming of the alkyl halide. So in order to name, you can just, if you already know how to name alkane, you follow the same rules because you don't have high priority. The priority of the halide is not more than the branches and is not more than the carbon chain. So what happens here, you can see that the numbering, it goes from the side that is closer to the branch, not closer to the halide. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know that we have a nonane, but you have to bring the branches first. when you are bringing branches, you number from the side that is closer to the branch, and it gives a smaller number set. But when you are naming the branches, you would name it in alphabetic order. Because bromo comes before methyl, you would say 6-bromo, 2-methyl, no name. Same rule applies. You are using a dash line to separate the number from letter, a dash line to separate number from the letters. But between the two letters, you don't have to use a comma or a dash line. The longer carbon chain takes priority, okay? Even though if you have a halide, longer carbon chain takes the priority. This is different from alcohols, different from the from like an alkene, because in this case, it's just the halogen versus long carbon chain. So if halogen had taken the priority, you would have to go 1, 2, 3, and then go to the other branches or other continue on the branch. But in this case, we are taking the priorities over the carbon chain, and you would start from either side. It would be number 4 for this branch. You would number the number assigned to the branch is 4, and then to give the complex name for this branch. This branch is an ethyl, but there's a fluoro attached to ethyl, so it's going to be 2-fluoroethyl. So when you are numbering a complex branch, you want to make sure that you number, you use number 1 for the carbon directly attached to the main carbon chain. So this takes carbon 1, not carbon that is directly is attached to the halide. Carbon that directly attached to the main carbon chain. So we have a main carbon chain here. That's the main one. And the carbon that is attached directly to it is going to take the number 1, and then the numbers increase. So it's a 2-fluoro and 2-fluoroethyl. So this group is called 2-fluoroethyl, as we have the spelling already here. And that is attached to carbon number 4. And we have a fluoroethane. It doesn't matter, you know, in this case, you have the chloro, it doesn't matter which way you number it. It would always be, you know, fluorine on carbon 1. So you don't have to say it 1. When you have this is for ethane, okay? It doesn't matter which carbon takes the fluorine, is going to be fluoroethane. So either side. But when you have more than 2 carbon, you have to specify is the chlorine or halide is in which carbon. So you have to use a number. So for 1 and 2 carbon chain, you don't have to give the number. Is understood. For methyl fluoromethane is always same. But and fluoroethane the same. If fluoro is attached to carbon on the left or right, would be number 1. You don't have to say it is understood. But for more than 2 carbon, you have to give the location to the halide. So we have 4 carbon and chloro attached to carbon number 1. It would be 1-chlorobutane or 2-chloropropane. And if it's a cyclic system, then you have to, for the cyclic system, I hope you remember from chapter 3, I just want to emphasize here, if you have 2 branches only, it doesn't matter which one takes carbon 1, right? The other, like if this was carbon 1, the other one would be 3. If one branch is on 1, the other one would be on 3. But if you have 2 branches that they are not identical, you have to go with the alphabetic order. So because chloro takes priority over methyl, the carbon 1 is going to be the one that is attached to chlorine or carries the chlorine, 2, and then 3. So it does make a difference. Chloro is going to be on carbon 1, even though the number set is the same. You are going to have 1 branch on carbon 1 and 1 branch on carbon 3. But it should go with the alphabetic order. If it's just 1 branch in cyclic system, you don't have to number it, just like ethane. it's understood that it's going to be on carbon 1. So iodocyclohexane, you don't have to say 1 iodocyclohexane. Any questions? Questions?
No.
Okay. For numbering of this, for numbering main carbon chain, we have 1, 2, 3, 4. We have a couple options here. From 4, we can go down to 5 and 6, or we can go to 5 and 6. Which one should I use? Should I go straight to the left, or should I go down for 5 and 6?
Whatever is shorter,
Let's
right?
go straight
Is
first,
it-
but we could do both.
Okay. Is there a point of difference here? So let me just go straight, 5 and 6. The other option would have been 1, 2, 3, 4, 5, and 6. So I have to see the difference. If you go down, you get the same number of carbon, and we are always looking for the longest carbon chain and not the shortcut. Okay, we are looking for the longest carbon chain. If
We
I
gotta go with the one with more attachments, right? More substituents.
Perfect. Yes. If I go straight with the blue color, I'm going to have 1, 2, 3, and 4 branches. If I use the purple color, and go down, I'm going to have 1, 2, and 3 branches. That's the point of difference. So if I go straight, it gives me 6 carbon, and I go down, it gives me 6 carbon. Then the next concern is like, which one would give me higher number of branches? And I would go with the side that it gives me higher number of branches. Longest carbon chain, lowest number set, greater number of branches. Please keep that in mind. And every time we learn new family, we learn about new rule. So you have to kind of remember and build on it. So you just don't want to forget the basics. Longest carbon chain, smaller number set, greater number of branches. So we have to go to the, we would continue with the blue line, and we number it. And after we number it, we are going to name it. So we don't have to, okay, let's see. And when you name it, what would be the name for this compound? Quickly, if you can help me with that. What's the name?
2-chloro, 3-bromo.
Which one should come in first?
It's an
Bromo.
alphabetical order.
So it's 3
3 bromo.
bromo, 2
2-chloro,
chloro,
5-methyl hexane.
4-ethyl.
4 ethyl, 5
2
methyl,
hexane.
5 methyl hexane. Very good. So halogens do not take priority over the other branches. We still follow the same rules that we learned in chapter 3 for this. Okay. Sec-butyl bromide, these are common names. The IUPAC name would be 2-bromobutane. That's a sec-butyl. And then we have the T-butyl bromide. This is a common name. These are some unique name, and these are also common name. It's not IUPAC name, but it's accepted name for IUPAC also. So instead of saying like a trichloromethane, just says chloroform, like water. It's already, you know, is a known name for this chloroform. And then carbon tetrachloride, and for two halogens, two of the halogens with one carbon is like a methylene chloride. And then you have 3 halogens would be haloform in general. So you have chloroform. So if you have a CHBr3 is going to be bromoform. And if you have a CHI3 is going to be iodoform. So CHI3, it's like iodoform, bromoform, chloroform. And then you have the carbon tetrachloride, bromide, or in general, halide is a common name for it. Alkyl halides, they can be classified as primary, secondary, or tertiary. Since you already know primary, secondary, tertiary carbocation, it's kind of easier for you. If the halogen is attached to primary carbon, this is the primary carbon. How do we know this is a primary carbon? Because there is only one carbon-carbon bond. This carbon is attached to one other carbon only. This carbon is a secondary because it's attached to 2 other carbon. And carbon that is attached to 3 other carbon or has bond to 3 other carbon is a tertiary. So if the halide is attached to primary carbon, it's called primary alkyl halide. A secondary alkyl halide, the halide is attached to secondary. And in tertiary, halide is attached to tertiary alkyl halide. The reason we want to know this classification by heart, because you have to learn more rules about which one is going to be faster with like a Sn1 reaction or Sn2 reactions. And at that point, you don't want to still have a doubt, okay, is this like a primary or secondary? So you better know these already before you get into the discussion of is this Sn1 or Sn2. Dihalides, if you have 2 halogen in a alkyl chain, is called dihalide. A geminal dihalide, like twins, they are on the same carbon, that's geminal. And then if they are adjacent, one on each carbon, carbon 1 and 2, or adjacent basically, is called vicinal dihalide. So we do have geminal dihalide or vicinal dihalide. These are just new terms for the new family. Some of the applications for alkyl halides, they are used as the anesthetics. They are freon and pesticide. So if you look at these chemicals, so these compounds, you see the structure for these compounds, like DDT, of course, is a pesticide, is not used anymore, but it used to be used as a pest control. And then you have the freons, you have everything that is like halide. So we have why they're very versatile. They're used in industry for synthesis, and they do have like everyday application. Okay. So we learned that the bonds between carbon and halogen is a polar bond. So we have a positive and negative side to this bond is a polar bond. The degree of polarity is measured by this unit of D, the Y, and it has to do with difference in electronegativity and a distance. So if let's say mu, that's the unit for polarity. Polarity, change in that's distance times delta. Delta is the same thing as change in electronegativity. And this is the bond length or the distance between the two nucleus. Okay, so there are two factors that is going to affect the degree of polarity. And for that reason, chlorine is going to CCl is more polar than the CF, even though F has higher electronegativity, but the size of the chlorine or the factor for distance is affecting the polarity, and we get higher polarity overall, higher polarity for CCl compared to the CF. If it's a specific question, you have to know this. Otherwise, you want to know that the bond, carbon bond to any halide is a polar bond. It gives carbon a positive charge because halide is negatively charged. Halogens, they are, yes.
It's just backwards from the electronegativity, the bond dipoles.
Yes.
Okay.
So boiling point or physical property of the organic molecules, it depends on dipole. It depends on intermolecular forces as well as the molar mass. So if you compare alkyl halide to alkane, like if you have 5 or 6 carbon alkane, even though the molar mass, it can be comparable to a compound that has chlorine with every 2 carbon, it can compromise, or it can be comparable mass to a alkyl halide, but the polarity between the carbon and Cl is going to give different intermolecular forces. So for alkane, you only have van der Waals forces or London dispersion forces, but for alkyl halide, you have dipole-dipole interaction. And if you do have dipole-dipole interaction, that means that is going to be intermolecular forces are stronger. The stronger the intermolecular forces, higher the boiling point. So we do have high boiling point for alkyl halide compared to alkane. So it's significantly different. So because that's due to the dipole-dipole interaction that we have for polar molecules of alkyl halides. So we have some information about the alkyl halides already. We know how to name them. We know that they are unique. They are more reactive than alkane because they do have a polar bond. We looked at the nomenclature, if it's a cyclic or if it's open chain. We looked at the intermolecular forces, that is dipole-dipole interaction for alkyl halides, but there's London dispersion for the alkane and other hydrocarbons. Dipole-dipole is stronger. As a result, it would give a higher boiling point. How to prepare alkyl halide, we learned this in chapter 4. And you had a test about it. The reaction is a free radical chain reaction. It requires light and heat. So the mechanism of the reaction is based on a free radical intermediate that forms is a free radical, and a secondary free radical is more stable. More stable intermediate, faster the reaction, major product. This is coming from primary free radical, and primary free radical is less stable, and because it's less stable, is going to be slower, and it gives you minor product. So that's how you prepare these compounds. And if you have allelic free radical chain reaction. For the allelic one, the reagent that we used, it was a NBS, N-bromo succinamide, instead of the BR2, because we wanted control and controlled, and when it is controlled, is going to only do like allelic position. So we use like controlled bromination, and with the controlled bromination, only the allelic position is going to be brominated. And the reason allelic position is brominated, because if you have free radical formed in the allelic free radical, if you have like a primary allelic free radical, that is stable, as a lot more stable than primary free radical, is as stable as like a secondary free radical. So the reason for stability of allelic free radical is formation of the resonances, because resonances form, the more resonance forms, more stable the intermediate is going to be. And if you do have allelic, then you have at least 2 resonances. But if it's not allelic, if it's just a primary free radical, there is no resonance. But if it's allelic free radical, even if it's like a primary allelic free radical, this is going to form resonance and is going to get the free radical moved to the carbon 3 or carbon 1 in this case, and the pi bond would move. So there is, when you have this double arrow, you have resonance. So allelic free radical is more stable than the primary free radical, and more stable even than the secondary free radical. So the reaction is going to take place in the allelic position. How would you prepare alkyl halide? N-bromo succinamide, this reagent, if we have talked about it before, fine. If not, if you hear this for the first time, is abbreviated as NBS. This reagent is specific for allelic bromination. And the example of that is going to, we had it on the previous slide. So if you add that to this molecule, the only position that would take the bromine, it would be the allelic position. So this position is going to be brominated.
That'll be primary, right, Professor?
Allelic. This is the primary allelic. Yes, this
Yeah.
is a primary, but it's not a simple primary. This is a primary allelic. Okay, this is allelic primary. And if you have allelic position, you must use NBS in order to brominate only the allelic position. Because if you add BR2, BR2 can add to this carbon and this carbon instead of adding to the allelic position. It's going to break the pi bond, and it will be added to one bromine would be added to each of these carbons. If you want to brominate the allelic position, so this is like unique, that's why I emphasize on it. If you want to brominate allelic position, you must use NBS. What is NBS? NBS is a N-bromo succinamide. This is the reagent plus HBr, and gradually is going to release BR2 as BR2 is being consumed in the reaction. So as BR2 is being consumed in the reaction, it would be more of it, it would be released. So this is like a slow release of BR2, and it's controlled, because if it's uncontrolled, if too much BR2 is added at the same time, you could get bromine in this position, you could get in all these positions, they would all can get bromine, but if you're using NBS, only the allelic position would get the bromine, only this position, right, with NBS.
Thank you.
So we learned about the this reaction of a free radical chain reaction already from previous chapter, and this is an example that halogens in light, in presence of light or heat, it can replace one of the hydrogen from alkane. We don't deal with fluorination or iodination because this is too fast and this is too slow. The only reactions that in the lab are suitable to be used in the lab are bromination and chlorination. So we have seen those. Bromination is more selective. Chlorination, it happens like it requires less energy, it's exothermic, but bromination was endothermic type reaction, but it is very, very selective. Yeah, but right now we're just looking at, as a review, how to prepare alkyl halide. So we know that free radical chain reaction is one method to prepare alkyl halide. Another method to prepare alkyl halide is like, if you already know about alkene and alkyne, which you have not learned about yet, this coming in chapter 7. Alkene CC double bond, you add HX, that could be like HCl or HBr, and HBr is better based on the thermodynamic or the amount of energy needed. When you add is addition reaction. So what happens in addition reaction? You break a pi bond, because CC double bond, you have CC double bond. There is a sigma bond and pi bond. You break a pi bond, and when you break the pi bond, each carbon now is left with only 3 bonds. Then each carbon can take one new bond on to make it 4 bond again, because carbon must have 4 bonds. So you break a pi bond and you add 2 sigma bond, 1 hydrogen and 1 halogen. The net result is formation of alkyl halide. You can do halogenation of alkene, but if you do halogenation of alkene, you get a vicinal dihalide. If you start with a alkyne, which is a CC triple bond also, you do you add HX, 2 moles of HX, you break both pi bonds, and you can get the dihalide. In this case, you would get geminal dihalide. These 2 reactions, the reactions with the blue color is going to be covered again in chapter 7. And this one is chapter 9. Okay. But these are some of the methods that you can prepare alkyl halide with the examples showing here. The one reaction that I want you to be aware of, you may not see it anywhere else, is like you add PBr3, okay, PBr3, it would halogenate alcohol. It replaces OH with the Br. It's the reason I want you to be aware of it, because if you're taking, like when you're taking organic 2, when you're taking like MCAT, PCAT, this is very common question, and it's not covered like in multiple places. Is not referred to it like too often. So if you're adding phosphorus tribromide to alcohol, it can change that to alkyl halide. Is a bromination of alcohol or halogenation of alcohol. It's a very unique reagent again. The reactions that you can see from the alkyl halide, okay. Common reactions from alkyl halide is that halogen can be replaced this can be, halogen can be replaced by a nucleophile. Okay. If it's replaced by a nucleophile, basically you're doing substitution. You substitute halogen with a nucleophile. It's called substitution reaction. What is happening in this case, halogen is leaving, so it's known as a leaving group. And then the nucleophile is going to come in and form bond. So it's a replacement reaction or substitution reaction. Alkyl halide can also go through elimination reaction. In elimination reaction, the halide would leave as a leaving group. You get carbocation, and the carbocation is unstable. In order to stabilize carbocation, you remove hydrogen from adjacent carbon. So it's basically minus H and X. So halogen is leaving. You remove a hydrogen from adjacent carbon. And when you remove hydrogen, you're removing H plus. You don't remove H with the electrons. Those pair of electrons will drop in and form a double bond. So you end up with alkene. So you can get the substitution. So it depends on what you are bringing here. You can change that to alcohol. You can change to ether. You can change to, depends on what nucleophile you are bringing in. But in elimination, you would always get alkene. If it's an alkyl halide, you would get alkene. If it's a dihalide, you could get alkyne. So in electrophilic substitution reaction, the electron withdrawing group is going to replace by another group. In elimination reaction, halide would leave, hydrogen would leave, and it would change to alkene as a result. Okay, if we have choice of iodine, bromine, Cl, and fluorine, all of these X's as a representation is considered as a leaving group. Which one do you think is a better leaving group? Chlorine or bromine? Which one is the better leaving group?
Probably
Bromine.
bromine.
And could you explain why bromine is a better leaving group?
You said that chlorine was a better binding.
No, but bromine is more
What's the difference
sensitive.
between them? Chloride or bromide? Which one is a better leaving group? Bromine is the answer. Yes, bromine is a better leaving group, but can you tell me why bromine is a better leaving group? By any chance? Okay.
Is it because it's less electronegative or more? Has
Okay.
something to do with that?
Okay. So when chlorine is maybe let's look at the position of the chlorine and bromine in periodic table.
Bromine's less.
When chlorine and bromine, they're attached to the alkyl group, they are sharing electron, right? When they leave, they are not going to they are not leaving as a free radical. This cleavage is going to be heterolytic cleavage. That means it's going to leave as a Cl minus or Br minus. So it's going to take pair of electron and leave, pair of electron and leave. Now, if it's taking pair of electron, that now it has to be concerned about carrying that pair of electron. If you look at the periodic table, you have fluorine, you have chlorine, Br, and then iodine, right? And for fluorine, you have 2 energy level. For chlorine, you have 3 energy level, and for bromine, you have 4 energy level, right? As you go up, down, the size is increasing. So bromine is larger than chlorine because this is the barrier, like negative charge. Negative charge is going to be easier to be handled on bromine because bromine is larger size. So negative charge on a larger atom is going to be more stable than a smaller ion. Like H plus is not a good leaving group at all. H minus either. H minus, how could you have like H minus like walking around? Because it's such a small nucleus, 2 electrons on it, there's not enough force from the nucleus to catch that, to attract those 2 electrons. So it's just 1 proton. Now it's going to be divided into half to give like attraction to 2 electrons. So it's going to make it very unstable. So halide, or I'm sorry, hydride is not a good leaving group. So this is not a good leaving group at all. I'm going to emphasize on that, okay? Not a good leaving group at all. Same thing for like CH3 is not a good leaving group, because you can, if you take it plus charge, is not stable. If you take a negative charge, is not going to be stable. So not good leaving group. So this is not a good leaving group. And so hydride, alkyl group is not good leaving group at all. So I'm going to emphasize on that. This is at all. So you never look at these 2, hydrogen or alkyl group, as a leaving group. It has to be something different from alkyl group or hydrogen to be considered leaving group. And then when you do have a leaving group, and if you are comparing Cl and Br, Br is a better leaving group than the Cl, because it has a larger size. It can carry this negative charge easier. As a result, iodine is going to be better leaving group than the Br. And they are both better group than Cl and much better group than fluorine. Fluorine carrying the negative, even though it's like highly electronegative, it wants to have those electrons, but it doesn't like to stay on its own. When it leaves, it's going to be very unstable as a fluoride ion. It's very reactive. So you can look at that fluorine, not a good leaving group, because when it leaves, it's not going to be stable on its own. But bromide is going to be stable on its own. So it's not a good leaving group. Fluorine is not a good leaving group. Iodine is the best leaving group out of these 4. So you learn about some characteristic for a leaving group. So leaving group has to leave and take pair of electrons, and it has to be stable on its own. Nucleophile has to have either pair of unshared electron, or it has to have like negative charge in order to attack the nucleus of alkyl halide. Okay, the reason I brought that beginning of this chapter, because everything else you can study on your own. You can, you could read the book and you understand. But basic and something like as little as what does nucleophile means, if you understand that, it's going to make it easier for you to study this chapter. A nucleophile, meaning that it likes nucleus. What is unique about nucleus? What do you find in the nucleus of an atom? You find positive charge. And opposite charges, they attract. So in order for something to act as a nucleophile, must have that negative charge, because nucleus already has positive charge. So when we say a nucleophile is going to like positive charge from the nucleus and is going to attack, and it can form a new bond. So why this X has to leave? What is wrong with X being there? If nucleophile comes in, what would be the problem? Can we just bring the nucleophile and keep the X?
No, because X would leave because the nucleophile would bring the other electron, correct?
Mm-hmm. So what would be wrong if the X stays?
Too many electrons.
Too many electrons for what? For nucleophile, for halogen, or for the carbon?
Carbon.
For carbon. Carbon cannot have more than 4 bonds. Carbon cannot handle more than 8 Electrons, because it doesn't have room. It's like you have like a 1-bedroom apartment and you cannot have a family of 4 as a guest staying overnight or over week. It's not easy because there is not enough room. You know, there's not enough room. So carbon has only S and P orbital. In second energy level, you have carbon with the 2s and 2p only. 2s is 1 orbital, 2p is 3 orbitals. So we have 1 and 3, 4 orbitals all together. And the maximum number of electrons is going to be 8 electrons. So if you want to put like the carbon in the worst situation, force a 5th bond, force a 5th wheel. You cannot do that. You have to make sure that somehow a weak bond has to break. So carbon cannot have 5 bonds at all. It's not going to be able to survive with 3 bonds either. Carbon is a tetravalent atom. It's happy with 4 bonds. Those 4 bonds could be in form of double bond, triple bond, or single bond. But when you count each dash line, it should add up to 4 bonds. So when nucleophile comes in, a leaving group has to leave. Now, this can take in different pattern. It could, leaving group can leave first and then nucleophile comes in, or as nucleophile gets in, leaving group leaves simultaneously. And depends on which of these 2 situations or pattern would take place in a reaction. You are dealing with 2 types of reaction. It's called Sn1 and Sn2. So you would have Sn1 reaction, Sn2 reaction, depends on what. If leaving group leaves first and then nucleophile comes in, that's going to be Sn1. If leaving group comes in at the same time that leaving group is leaving, nucleophile comes in, then you would have Sn2 type reaction. So depends on the pattern. And that's the major part of this chapter, to study the pattern. Is it Sn1 or is it Sn2? What factors affect the reaction to promote Sn1 condition or Sn2 condition? And what is going to happen if Sn2 takes place versus Sn1? So nucleophile comes in, leaving group leaves. The net result is called substitution reaction. Nucleophile substitute the leaving group. If the carbon halogen bond breaks first, so you have intermediate, you have carbocation, then the nucleophile comes in and reacts with the carbocation. The net result still is alkyl nuc. So you get your substituted product. And here is happening at the same time. So you have both of them like engage at the same time. One is leaving, one is coming in, but here one leaves first before nucleophile comes in. Leaving group would leave first before the nucleophile comes in. So what is happening in the reaction, or how do you study the reaction and decide what is happening? Is it the leaving group leaving first, or the nucleophile comes in and the leaving group leaves at the same time? If you study a reaction based on the rate of the reaction, if you study rate of the reaction, you can decide what is happening. Do you have like 1-step reaction, or you have like 2 steps reaction? So for a reaction that alkyl halide is coming from like a primary alkyl halide, okay? So if you have a primary alkyl halide, this is like experimental finding. You have methyl bromide, ethyl bromide, propyl bromide, and then you have your secondary and tertiary, okay? Secondary and tertiary, and you look for the experimental value. The rate of the reaction is much faster with methyl bromide, 1,200 times faster than if you were dealing with a secondary alkyl halide, and forget about the tertiary alkyl halide. Okay, forget about the tertiary alkyl halide. So this is one set of experimental values that first you collect data, then you analyze your data, and you come up with explanation. Well, someone else has done all the study, and they are showing here that how they actually, where did they begin? How did they come up with this idea that if this is happening, if you see that the rate of the reaction for methyl bromide is 1200 times more than a secondary, the mechanism of this reaction must be Sn2. Because when you look at the kinetic for the reaction, in Sn1 reaction, let me see if I can just use the whiteboard, or I need the whiteboard here. Okay. So I'm going to look at this transition state, and then on the whiteboard, I draw the energy diagram for you. So what is happening in this case, in this example, you have your nucleophile, okay? Your nucleophile coming, and you have your leaving group. The bracket, the green bracket, and this sign that it looks like this, it shows like a 2+ sign here. This is showing transition state. The transition state is an unstable situation here. Why is unstable situation? Because carbon has like too many bonds. It looks like carbon is having like 5 bonds. It's a transition state. If you have like a house, you sold the house, you haven't left, the owner is coming in with the furniture. So everything is happening at the same time. It's a lot of pressure, it's a lot of excitement, and everybody.
So pretty much it's like the moving phase from
Yes.
one point to another. It's the middle part.
Is the middle part, but it's
Okay.
both of them is happening at the same time. The seller is leaving, the buyer is moving in at the same time, and it makes it very unstable. And if it's very unstable, that means the energy is very high for the compound in this stage, which is called the transition state, is high. So when this bond, it gets loose, the leaving group leaves, and then the hydroxide forms a solid bond. Now you have your product. So the pattern in this case is that nucleophile comes in and leaving group is leaving at the same time. So at one point, both of them are involved in the reaction. So if we draw the energy diagram for this, it might make more sense to you. So let's say I have reactants, and then in reactants is going to the product. In transition state, that is where you have the nucleophile is coming and leaving group is leaving. So you have your reactant and you have your product. We learned that in chapter 4 that this is called activation energy, EA. And we learn now that this is the transition state. Okay, so you have your transition state here. How many steps do you see in this reaction? It's just one step, right? There's a one-step reaction. So if I draw this reaction here, I have this reaction. It's two-step reaction. So I have EA1 and EA2. EA2. One-step reaction. This is a two-step reaction. So which step is rate determining step for A?
There is none.
That would be a silly question, right? Because there's only one step. So that's the only step.
Professor, don't be throwing out trick questions now.
Okay, so you have you have only one step reaction here. So that's the only step. So that step is the rate determining step. How would you write the rate law for this reaction? A rate law for this reaction general rate law, rate equals K times concentration of the first reactant times concentration of the second reactant. What is the first reactant? If you look at this reaction, you had the nuc plus Rx, right? That gives you nucleophile R plus X. Okay. So the first reactant and the second reactant, so we have the Rx and the nucleophile. So both concentration of both substrate, the alkyl halide is known as a substrate also in this reaction, in substitution reaction, and the nucleophile, both of them are involved in rate determining step. So if you increase the concentration of alkyl halide, rate goes up. You increase the concentration of nucleophile, the rate goes up. That experimental value can show, based on what you learned in 1046 and chapter 4, that when this happens, you know this reaction depends, the rate of this reaction depends on both reactant. So both of these reactants, they are involved in the rate determining step because both of them are involved in the transition state, which is the activation energy reaching to the transition state. And that is going to determine the rate of the reaction. So for your reactant to go to product has to overcome the activation energy, has to reach the transition state. And in the transition state, you have both leaving group and the Rx, both the nucleophile and the Rx involved, or both leaving group and nucleophile are still attached to the carbon. If you look at the diagram B, you have two-step reaction there. Which step is the rate determining step for B?
First one.
First one, because in the first one, you have higher activation energy, or first step is the slow step of the reaction. So we have a slow step and fast step. Okay, slow step is the rate determining step. And what is happening in this step is that you will get Rx would change to R plus the X minus. That's the first step. In the second step, you get the carbocation plus the nucleophile, and it gives you R nuc. So you get the product.
Why would it be R plus?
Because when X leaves, it's going to take pair of electron because X is minus.
Correct.
And then
Oh, and the carbon becomes positive?
Carbon becomes positive, yes.
Okay. All right.
Okay. But so you have two steps. In the first step, carbocation forms. In the second step, carbocation reacts with the nucleophile and you get the product. So if you were going to write the rate determining step for this, the rate law for this reaction, you only write the rate law based on the first step of the reaction, not both steps, because only a slow step is going to determine the rate of the reaction. What is involved in the slow step of the reaction is only the alkyl halide that is going to change to carbocation. The nucleophile, which is the second one, is not involved in the rate determining step. So it's not going to show up in the rate law. So you don't have to write the concentration because it's not going to be there. So for two-step reaction, the rate determining step is the slow step of the reaction, and the rate law only depends on one of the reactant. For one-step reaction, both of them are involved. So only one involved in B, one reactant. In A, you have two reactants involved. The abbreviation that is used for A and B is called substitution, nucleophilic, and then it says 2. Basically, it says unimolecular nucleophilic substitution reaction. Why unimolecular? that means that both nucleophile and the alkyl halide are involved in the rate determining step. And how would you modify that for diagram B? How would you modify it? Instead of SN2, what should I say here?
SN1.
SN1. And what does it mean? It means that in rate determining step, only one of the reactant is involved. Yes, the changing concentration of only one of the reactant would change the rate of the reaction. So the rate of the reaction depends on only one of the reactants, not both reactants. So it's called unimolecular. So this, did I say uni for two?
Yeah.
Can I take it back?
Maybe.
So we have unimolecular, that's for one, and bimolecular is for two. Sorry. So
Professor,
unimolecular nucleophilic substitution for one, for SN1, and bimolecular nucleophilic substitution for two.
so any multi-step reaction is always SN1?
In a multi-step reaction,
Yes,
you have to find the rate determining step.
correct.
And if in rate determining step, you only have one of the reactant involved, then that would be the, if it's only one reactant, then it's going to be SN1, yes.
Okay,
And if it's substitution reaction would be SN1. Now, if it's elimination reaction, you don't say S, you would say E. For elimination reaction, if it's two-step, and you get only one of them involved in the rate determining step, then it's going to be E1, elimination, but based on the mechanism of the reaction, only concentration of only one of the reactant is important, or it's going to affect the rate of the reaction. So we have E1. And what would be E2? E2 meaning that both reactants are involved in the rate determining step. So those are the four mechanisms. They are known as four mechanism. Is probably, you know, the most challenging part of organic one. Everyone would remember it, but there are like a lot of great videos that they would say it in different language. It's going to make it easy to remember, and you learn it once and you remember forever. This is the part that is very hard to forget. At least like SN1 and the SN2 reaction. They say it's very, when you learn it, it's very hard to forget. And depends on how you learn it. So,
Professor, I have a question about one of the graphs here. So SN2 it involves both reactants because you have the leaving group and the nucleophilic doing the thing at the same time.
yes.
So that those would be both of the reactants.
Mhm.
Okay.
And for SN1, one reactant, which is your alkyl halide, is going to go through the first step of the reaction, which is this step of the reaction here, and is going to lose that leaving group, changes to carbocation. So that's your first step. This is the first step.
Okay.
Okay. And that is the one with the higher activation energy. And that step is rate determining step. And that's why when we write the rate law for this reaction, we only make the Rx part of the equation and not the nucleophile, because nucleophile comes in the fast step. And we learned from kinetic in general chemistry too, that if you have multi-step reaction, only the slow step of the reaction is going to affect the rate of the reaction. Like if your exam has two, if a course has only two exams, one very hard exam and one very easy exam. Which of the exams is going to determine how many people would pass the course is the hard exam, right?
Yeah, you would choose the harder one.
If any student would pass the hard exam with the same effort, would definitely pass the easy exam. So So it depends on there are two obstacles, but one is much harder than the other. So if you get the hardest one out of the way, the easy one is easy. And it will happen with the amount of energy that you have to pass the first one, the hardest step. The easiest step would happen on its own. That's
Gotcha.
why they say the fastest step doesn't determine how fast the reaction is going to go, is the slowest step that is going to determine how fast or how slow the reaction is going to go.
Thank you for that.
You're welcome. So next, we have a diagram here that compares two of the two reactions. Both of them are SN2. Both of these are SN2. Now, one of these is faster than the other. So we have to look for the point of difference. What's the difference between diagram A and diagram B? In diagram A, we are dealing with methyl bromide. Okay. In diagram B, we are dealing with a alkyl halide that it's not methyl. You have two R groups or two alkyl groups instead of the hydrogens.
So wouldn't it be A?
A is faster, right? A
Yeah.
is faster. There are multiple reasons that you can use to say A is faster. The one that is kind of obvious is to look at the activation energy, EA, for reaction A compared to EA for reaction B. This is one step, so we are not going to say which step again is the rate determining. There is only one step. So we know based on the energy diagram that A is going to go faster. And for both of them is one step reaction. Now we have to look for point of difference. What is difference here? For your nucleophile, of course, the strength of a nucleophile is important, but your nucleophile is OH. Your nucleophile here is also OH. The nature of the leaving group is important because the better the leaving group, the faster the reaction, but your leaving group is the same from A to B. Leaving group is also the same. Both of them are SN2 reaction because it's one step reaction. And if you look at the transition state, you see that leaving group is leaving, the same time nucleophile is coming. So what is the point of difference here is that for A, you have two hydrogen attached to the carbon. For B, you have bulky groups attached to carbon carrying the Br. So if you have like bulky groups here instead of the hydrogen, would that make harder for OH to come in? Compared to hydrogen? Definitely, right? And that term is something that is going to be very important for this chapter. It's called a steric hindrance. A steric hindrance is a significant factor for SN2 type reaction. This type of reaction is SN2 because we know that both nucleophile and the alkyl halide is involved in the rate determining step. So we know this is SN2. And this one is also SN2. But SN2A is much faster than SN2B because SN2B has a steric hindrance. What is causing the steric hindrance is the alkyl group that is attached to carbon with the Br. Now for OH to come in, it has to push away those alkyl groups and say, can I get in there, please? But when the groups are hydrogen, hydrogens are not that bulky and they are not actually on the way for hydroxide to come in. They don't cause much of a steric hindrance. They cause a little, but not much. The bulkier these groups are, the slower the reaction is going to be. If it's SN2, just keep that in mind. If it's SN2, you have to look at the steric hindrance as a significant factor for the rate of the reaction. If it's SN1, that is a different story. We will look at it later in like a couple of slides down.
Would it be like opposite for SN1? I'm guessing.
It would be opposite with different definitions, with different explanation. Yes, but it would be opposite. So if your alkyl halide is a primary alkyl halide, is going to go faster than the secondary. Now, with that diagram and explanation about the steric hindrance, probably these numbers make more sense to you. So if you have a methyl bromide, it's going to be 1200 times faster than isopropyl bromide, because for isopropyl bromide, for the chloride to come in, is going to be hindered by these two methyl group. But for methyl bromide, these are only hydrogens, so you don't have that that steric hindrance. So it should make sense now. That significant, 1200 more times.
So basically, the more groups and the more bulkier groups, the more slow it goes.
The slower the reaction. The bulkier the groups attach, the slower the reaction.
So it's kind of like, for me, how I remember it is eating a meal. Like if you eat a large meal, you end up getting tired quicker. So if you eat a small meal, it's a little bit faster for your body to digest. I mean, that's how I'm remembering it or looking at it.
Okay, that's great. And another example, actually, you talked about the food. Now, if you have your plate, okay, if you have your plate and there is a buffet, you go to a buffet and then is a buffet style of serving food, you have your plate and you go there, nobody is there, you get your food and you leave, right? But if you have your plate and you're hungry and you're ready to go and take the food, but there are like 4 people in there, they're taking food. And is it going to be as easy? It's not going to be as easy, because reaching to that serving spoons and utensils is going to be harder for you now, because 4 people already are using it and there aren't enough room for you to get in. Does it make sense?
Yes.
Okay, so it's going to be faster if it's less bulky, because reaching into the center, which is the food in that case, is easier reach to the food, compared to if you have like 2 people, or if you have like 3 people, or if you have like 2 or 3 lines that they are using the utensils, and then you have to actually wait in line for those lines to get shorter, then you can get in there. So that can kind of explain the steric hindrance as well. So the bulkier the group, the slower the reaction. This is for SN2 only. And we can see that. Yes.
I had a question. Does esoteric hindrance play a bigger role than, let's say, if you had a stronger nucleophile?
Yes.
Esoteric hindrance has more of an effect.
Yes, it has significantly, yes, higher effect than the strength of the nucleophile is also
It's
very
not negligible.
important. It's not negligible at all. That is very important. You must have very strong nucleophile. You must have a strong nucleophile for SN2. If you want faster reaction, it must be a strong nucleophile. For the same example of someone with a plate on his hand trying to get to the food, just imagine that person being shy and or not hungry. What's going to happen? It's going to wait there. It's going to wait there until everybody gets their plates filled up and leave, and then is going to come slowly. But if it's someone who is not shy at all and also hungry, and that makes like a person who wants to reach to that food faster, right?
Yeah.
Like a stronger nucleophile. So if you have a stronger nucleophile, you might get in there and say, "Excuse me, can I get one of these? Can I reach to the food?" You might actually say that. You might actually push someone. Depends on how aggressive you are and how hungry you are. But if it's the opposite, you're going to be very slow, and that reaction of getting food is going to be very, gradual and very slow. So yes, good point. That's the secondary factor, but it is a important factor, the strength of the nucleophile.
Gotcha.
And also the leaving group, how good the leaving groups should be. If the leaving group is not good, is not a good leaving group. Some people, they take food, they leave. Can you imagine someone who is like standing there trying to get this food and then taste it, don't like it, put it back, or put back my plate and then get a new plate, and then I get different food. And it depends on how hungry you are. It can make you very, it's going to take longer. It's going to take longer because the leaving group is not a good leaving group, because it doesn't take the food and leave. Staying there, talking to friends, and is not maybe like hungry, or doesn't want to have someone waiting in on the table for them. So they're just taking time. That type of group or the person is not going to be considered as a good leaving group, right? It's not going to leave that table. It's not the so the nature of the leaving group is important as well. So you have the steric hindrance effect, you have the nucleophile, the strength of the nucleophile effect, and then the nature of the leaving group is a big factor. Lastly is the solvent. Solvent also is going to affect the rate of the reaction for SN1 and for SN2. So let's look at some numbers and we move to the next slide. We talked about the bulkier the group. You see, you have only hydrogens for methyl bromide, and then for ethyl bromide, you have hydrogen and you have one methyl group attached to that carbon. So it drops significantly. You are going from ethyl group to propyl group, so the group is bulkier. This is like a longer line waiting, and the slower the reaction is going to be. And if you have like two groups rather than one long group or one bulky group, the number of the group attached is going to make a more significant, is going to count as a more significant factor. Number of the groups takes the priority. And then it goes to the size of the group that is going to affect the rate. In a way that if you have three groups, so for tertiary, forget it, it's not going to happen. Very slow to measure. So for SN2 reaction, configuration is going to be inverted. This is called Valden inversion. So configuration is going to be, this is only applicable to center that is a chiral center, is attached to like 4 different groups. Now, if the leaving group is showing that is leaving from the right side, the hydroxide ion is going from the left side, basically opposite side of the leaving group. So the orientation or the configuration is going to be opposite, because now your heavy group is going to be in the opposite side. You might say, well, why the nucleophile is not coming from the same side? And I'm sure you do have the answer also. The nucleophile has negative charge. The leaving group has negative charge. The negative charge means that is rich in electron, high density of electron, high density of electron. The electrons, they repel each other. So why would this OH go from the same side that Br is leaving? Is going to make it very uncomfortable, because it's not going to be attracted, it's going to be repelled. So OH is going to act smart, and it will come from the opposite side, is called the back attack. And if it's coming from opposite side, it's going to bind from the opposite side. It's not gonna come attack from the opposite side and then bond from the other side. It doesn't make sense, right? So because it's the heavy group or the high priority group now is changing position to the exact opposite side. If you start with R, you end up with S. So in SN2 reactions, you will get configuration inverted. If you start with R, you go S. If you start with S, you will go change to R, and is known as like an umbrella effect or Valden inversion that is happening. You see this, like if you have the umbrella is pointing the other way. So it's kind of changing the configuration completely. So you get, you know, terms, different books, they call it differently. Looking at a different factor now, which one is going to move faster? This, you see, all conditions are the same. You are dealing with the same alkyl halide. You're dealing with the same nucleophile, but the leaving group is different. If the leaving group is different, the better the leaving group, the faster the reaction. Fluoride is not good leaving group at all, so it's going to make the reaction very slow. And what type of leaving group is going to be better leaving group? It's like if you end up with like a weak base, is a better leaving group. Which one is a stronger acid, HCl or HBr? Which one is a stronger acid?
Yeah.
Which one?
HCl.
If you go up down in a group, the lower you go, the acidity is going to increase. Actually, HF is known as a weak acid. This is a strong acid. HBr is a strong acid, but HBr is stronger than HCl. HBr is stronger than HCl. So after changing to a base, after losing hydrogen, it's going to change to conjugate base and is going to change to conjugate base. So acid, the stronger the acid, the weaker the conjugate base is going to be. So a weaker conjugate base is a better leaving group, is more stable. A strong base, meaning that it's looking for H+ to attach. Weak base, meaning that is more relaxed, so more stable on its own. So the other factor that we talked earlier is the size of the BR compared to the CL. BR is larger than CL, is a better leaving group, is more stable on its own.
So in that scenario, HI will be the strongest out of all of them.
HI is the strongest acid, and I- is the weakest base, and I- is the best leaving group. Yes, you're right.
So it goes back to the electronegativity thing, right? Where fluorine was the strongest, but then if you flip it backwards, it's the opposite.
Yes.
I think it has more to do with size.
The size factor. The size factor. So size and electronegativity is kind of the opposites, right? So it's like more of a polarizable. Like iodine is more polarizable, so it makes it a stronger acid. And then I- is a weaker base, more stable. So you can look at it as like a different view, but either one would work. So let's look at some of the leaving groups, that they are good leaving groups. For example, you could have chloride, bromide, iodide, or sulfonate. These are, or sulfate. These are leaving groups that they have negative charge. And then you could have neutral molecules like water, alcohol, or amine, that they are leaving groups. You see, you don't have OH part of those. Not a good leaving group. You don't have a H+. You don't have CH3 or alkyl group, part of the leaving group. These are not leaving group. This is a leaving group, but not good leaving group. Okay, it's not a good leaving group. and these are not leaving group at all. But you do have some of these examples of the leaving group. So we looked at two factors already, the primary, secondary, tertiary. So it depends, primary would go through SN2 faster than secondary and much faster than tertiary. The nature of the leaving group, the better the leaving group, the faster the SN2 reaction. Like in either case for SN1 and SN2, because leaving group has to leave, the better the leaving group, the faster the reaction is. But at least for each one of them is a major factor. Like it's not the primary, but is a major factor as well. A stronger the base, okay, the strong base, it counts as a strong nucleophile, and then weak base is a weak nucleophile. So this tertiary, the third factor that we talked about before said like how hungry the person is staying in the food line is like, or how aggressive it is the nature of the nucleophile. The stronger the nucleophile, the faster the SN2 reaction. But how would you recognize if the nucleophile is strong or not? Sometimes a strong base is a strong nucleophile. Comparing, so you're just comparing the two. Let's say you're comparing water with hydroxide. Which one is more aggressive? Hydroxide is a better nucleophile compared to H2O. H2O is a weak nucleophile. Alcohol is not a good nucleophile. It's a very weak nucleophile because it's stable on its own. It doesn't have to go and react with something else. But if you remove H from alcohol and you change it alkoxide, now it becomes very aggressive and it has a negative charge. So it is a strong nucleophile. You have a weak base, NH3, you remove hydrogen, you're going to make very strong base out of that. So it's going to be a strong nucleophile. So a strong base in general is a strong nucleophile. Questions? Okay. So just comparing other nucleophilic effect, which was better nucleophile, iodine or fluorine, even though fluorine is highly electronegative and likes to, have electrons, it doesn't like to share electrons as much as the iodine. So iodine is a better nucleophile than the fluorine. Fluorine is a weak nucleophile. It doesn't want to share electrons. It wants to take electrons, wants to absorb electrons. So this factor is known as the polarizability. That's going to affect the strength of the nucleophile. Iodide is a stronger nucleophile compared to fluoride. Solvent effect, polar protic or aprotic solvent. Which one is best for the SN2? For SN2, polar aprotic solvents are better. Okay. Those are the solvents that they do not have ionizable hydrogen. Like water is polar and is also protic. Alcohol is polar and it's also protic. But if you look at acetone, acetone is polar because you have the CO bond that is polarized here. You have negative and positive side to the molecule, but is aprotic. So aprotic polar solvents are good for SN2 type reactions. So like very specific cases that in a protic solvent, the weaker the base, a better nucleophile. It's going to take a lot of memorization, but it's something that when you learn, it's hard to forget, at least. So the sooner you start working on end of the chapter problems, and for end of the chapter problem, if you do like every other problem, it's better than to do all problems for the first 40 and then forget about the last 30 questions. But if you do like every other problem to begin with, you get more chance for the start covering the entire chapter, and it's going to help you better for assignments. And then you do the assignments, check the assignments early. Do not wait for the last couple days. You still have 2 weeks time before your exam, and now is the time to start, especially for this chapter. Start as early as possible for practice problems. Do you have any questions for me at this point? So this is kind of tricky. Is not going to be very, you may not need to memorize it right now. Over the time, as you solve problems, it will kind of becomes more natural. But it depends on your solvent. If the solvent is polar, weak base is better nucleophile. If the solvent is non-polar, then a strong base is a better nucleophile. Because if the solvent is polar, a strong base is going to react with solvent rather than attacking. So that's the difference. So you can see that a nucleophile in the strength of the nucleophile, but definitely if you have a neutral compound, it's not going to be a strong nucleophile. Like alcohol compared to alkoxide is not a good nucleophile. If you learn, as the slide covers, two cases at a time, like between fluoride and chloride, which one is the better nucleophile? Definitely chloride would be better because it's more polarizable. Compare bromide with the chloride, bromide is better. So you don't have to memorize the whole set. Like iodide is better than bromide and chloride, and you won't get a question to line them all in order, really. But you could get a question to compare chloride, bromide, and iodide, which one is a better nucleophile. Because of the polarizability of the iodide is a better, and that can be expanded to bromine and chlorine compared to the fluorine. Fluorine has the lowest tendency to share electron, so it's not a good nucleophile. So if you want make like, this is a specific case that you want to make the fluorine to better nucleophile or act as a nucleophile, don't stay with the potassium. So bring in potassium fluoride, and you bring in a polar solvent that is aprotic, is going to like a DMSO, that is dimethyl sulfoxide. Okay, DMSO, dimethyl sulfoxide. You have a methyl group, and sulfur oxygen is called dimethyl sulfoxide. It can solvate or take the potassium and stabilize the potassium what happens to fluoride? Fluoride is going to leave potassium because potassium now is taken by the solvent. So fluoride has no choice but looking for another positive center, and then it will attack a carbon with the positive charge. So it makes the fluoride better nucleophile. That's basically what it's trying to explain. If you have a bulky group, if your nucleophile is very bulky, it's going to be least a favorite for Sn2 because of the steric hindrance. So the less bulky it is, the better nucleophile is going to be for Sn2 reaction. We can take it that way. It's the less bulky alkyl halide and less bulky nucleophile is going to be better nucleophile. Okay, is this going to fast reaction or slow reaction if it's Sn2? If Sn2 is going to be fast or slow?
Slow.
Slow.
Very slow, right? Because you have all these groups attached to it, it's going to be very slow. But this reaction actually takes place because what are the other problems with if it's Sn2? And why is slow? First factor is that tertiary, so it's going to go slow. What's the other factor that you could see that is going to make Sn2 reaction slow? What do you need for a good Sn2 reaction? You need a alkyl halide that is not hindered. So you need like a primary alkyl halide. What else do you need for Sn2 reaction to go fast?
Strong nucleophilic.
Very good. A strong nucleophile. Is this nucleophile strong or weak?
It's pretty weak.
Pretty weak. Can you identify your nucleophile? Which species counts as a nucleophile here?
The H2O.
H2O. So your nucleophile is very weak nucleophile. So this is a weak nucleophile, and this is a bulky alkyl halide. So Sn2 is going to be very slow, right? Very slow Sn2. So if it's Sn2, it's going to be very slow. But since this reaction happens at room temperature, no energy is needed. It's going to go to alcohol. The reaction is called like solvation. OH is going to replace the bromine. There must be something else. So if it's not Sn2, if it's Sn2 and it's not happening, so it must be a different mechanism. And that different mechanism is called the Sn1 mechanism. That means that bromine is going to leave first. It would change to carbocation, then the other group would come in. And since I want to make sure that you at least know one mechanism. Before we talk about the second mechanism, I'm going to stop the lecture here. I will answer your questions, but I don't want to put too much information. We can look at some of the examples, but this is just, they're trying to say, how did they come up with the Sn1? Says, okay, this is happening, this reaction happening, but everything is against the conditions that we set for Sn2 to be fast reaction. So it must be Sn1 reaction and not the Sn2 reaction. Okay, your questions. Your questions?
I think we're good.
You're good? Okay. So you see this other set of data? as is showing in this table, your tertiary is going much faster than the primary, much faster than secondary, and then secondary much faster than the primary, because the mechanism of the reaction now is different. Is not SN2 anymore. This is a SN1 reaction. In SN1 reaction, you have your tertiary much faster than secondary than the primary, because mechanism of the reaction is different. Here we want bulky groups. We want the bulky groups to be there. We want the steric hindrance. We don't want it. The person or the species that actually want it is the carbon with the positive charge. And the more R groups you have attached to it, and you cannot have like more than 3 R groups, basically, the more R groups you have, the more suiting condition is going to be for this carbon that is electron deficient. The reason for that is that experimentally, or based on the experiment or experience, has been found that R groups are electron donor group. These are, they are not electron withdrawing, so these are donor group, electron donor. So they can give electrons, they can provide some electrons based on the, sharing the sigma bonds or hyperconjugations, or they can just support the plus charge on the carbon. So the more R groups you have, the better, more stable the carbocation is going to be.
Professor,
so
with
you have
the
a
stronger,
carbocation intermediate. Yes.
if you attached a stronger one, let's say like if you took the tertiary and you had another one next to it with instead of bromine you had iodine, that would be faster, right, than the bromine?
Yes, iodine leaving group is going to favor both SN1 and SN2 reactions. So if you have a better leaving group, that's even like what is called a cherry.
Oh, it favors both of them, not just
Yes.
SN1.
For both of them. Good
Okay.
leaving group is good for both of them, because we want to replace that leaving group. The better the leaving group is, the faster reaction is going to be. For both SN1 and SN2, leaving group is being replaced by a nucleophile.
Okay, so just the esoteric hindrance is opposite for SN1 and SN2.
Exactly. Yes.
Okay.
We have the hindrance, the steric hindrance that you have for SN2, because the leaving group's still there, and nucleophile wants to come in. It needs some room to get in, and carbon doesn't want to have more than 4 bonds. It's going to just make it hard for the nucleophile to get in and reach that carbon with the positive charge. So the more bulky group you have, the harder it's going to get.
I see.
But for the SN1, because the leaving group is going to leave no matter what, the carbocation is going to form, and that is the step that determines the rate of the reaction. The more stable the carbocation is, the faster it's going to form. The more stable the intermediate is, the faster the reaction. More stable the product is, the faster it's going to form. So in this case, the carbocation counts as basically the intermediate or the product of the first step, because it's stable, is going to form faster, or the more stable it is, the faster it's going to form. Since I promised that I will not cover SN1, I don't want to move to next slide, because then that would be SN1 reaction, or this is the beginning of the SN1, but we talked about one factor at least, so you could compare it, what happens if it's SN1. Tertiary is going to go faster. Yes.
I'm sorry. If there's a question, would it tell you if this is a SN1 or SN2 reaction, or do you have to figure that out part by yourself?
The question could tell you for which one is faster for SN2, or which of these alkyl halides would go faster for SN1 mechanism. The question could be like one of the experiments in experiment 9, actually, that they say the solvent that you are using is protic solvent, like the water is used as a solvent. And on top of that, you're adding like silver nitrate, trying to stabilize carbocation. then the condition of the reaction is going to help you to decide that this is Sn1. But if they want you to decide based on the condition of the reaction, then you have to be given enough information. So it kind of makes it more very obvious that this is Sn1. Now you tell me which of these alkyl halide would go faster in this under this condition. But there are some conditions that are specific to Sn1, and that is like polar protic solvent. So if you see polar protic solvent, we know that is Sn1. If you have weak nucleophile like water or alcohol, it cannot go through Sn2 reaction. It's going to be Sn1. But if you have
okay, so it'll be good to look for like keywords like that to figure it out too.
Exactly. Yes, we are looking for the keywords here. Yes.
Professor, would a Sn1 reaction also change the SR orientation?
A good question. If you want, I can explain. What happens if you have carbocation? What's the hybridization of carbocation?
sp3?
No.
sp2?
Carbocation has only 3 electron domain, right?
So sp2?
SP2.
You have a sp2, and if it's a sp2, the center or the carbon is going to always have a anhybrid p orbital, right?
Mm-hmm.
So carbocation, when carbocation forms, it becomes like a flat molecule. So it comes planar because it's the sp2. It's not a 3D anymore. It's not
okay.
tetrahedral. Now it's like a trigonal planar. So it's like a flat surface. And if it's a flat surface with these 2 loops that you have on top in opposite direction, when you bring the nucleophile has 2 choices and it's kind of a 50-50. So kind of 50-50. And after, like I covered the slides for Sn1, I would tell you that it can go like a 50-48, but still is very close to 50-50, right?
Yeah.
So the nucleophile can go from the top, can form bond with the top loop or the bottom loop. And because there's a 50-50 chance, because this is a planar molecule, then it can give you a racemic mixture. So the product of Sn1 mechanism is a racemic mixture. That means you get 50% of the R and 50% of S, regardless of what you start with. You could start with R or S, but you end up with mixture of the 2 if you're dealing with a chiral center or chiral compound. Very good question. Okay, please let me stop the recording.